all very welcome, those new members. Hopefully they'll get to present here in the forthcoming period. I'll hand over now to Graham Benham, School of Maths and Statistics. He joined UCD on the 1st of May, so he's a very new staff member. Delighted to have him on board in the Institute. I'll let him say a little bit about his own research and some of the collaborative opportunities he'd like to pursue, maybe with new people in UCD.
Thank you. Yeah, I think I've got, yeah, thanks very much for the invitation to come and talk. So I'll try and talk for about 10 minutes, and then maybe we can chat a bit afterwards, but I've got to run away at 11 because I'm teaching a course in the Newman building. So I thought I'd talk about a few examples of things that maths can be applied to. So I did my undergrad in pure maths, which I really enjoyed. And then I got to the end of my degree and I thought that was really fun. What can I do with it? And so I started thinking about different directions I could go in to try and use some of the maths that I'd learned applied to something useful. So I thought I'd sort of walk through some of the problems I've worked on, also just as a way of introducing myself and getting to know you guys. So yeah, so I first of all, after finishing my undergrad, I started a PhD in Oxford, and I was looking at applying maths to optimize a type of hydropower called low head hydropower. And what that is basically is when you've got a weir, like on a canal, for example, you've got this pressure jump, right? But it's not very big. It's not like a huge hydropower dam. It's just a few meters. And so people are interested in how can you usefully harness energy from small head situations like rivers and tides. And so my PhD was trying to optimize the shape of this, what's called a venturi. And what a venturi does is it takes a flow and it accelerates it super fast. And as it does that, because of the Bernoulli principle, the pressure drops massively as it accelerates. And so even though you've got, let's say, 3 meters pressure drop, it can feel like 12 meters pressure drop. And it becomes much more efficient to harness that energy. But it turned out that to optimize this, you needed to understand the way in which these flows mix together in a turbulent way. And so what I did was formulated like a constrained optimization problem. I'm not going to go into the mathematical details, but basically you try and optimize the shape of the thing constrained by, there's a constraint that the physical equations have to be solved, basically. And then you can actually calculate a formula for the optimum angle of the venturi, which is 2.3 degrees. And so that actually got built then in 2018. So this is, that's me standing there with some of the members of my funding company, the company that funded my PhD. And the venturi is sitting in the background there. That's that great big blue thing. And so that venturi is now sitting beneath this pub in Cambridgeshire. So it generates electricity that powers the pub, but then they also sell the electricity to the grid. So you can go there and have pints which are actually powered by maths. So then after that, I went and did a postdoc in Paris, and sort of a slightly similar theme on shape optimization. So I was working on this project that was sponsored by the Olympic Games. So the French government basically, for the last decade or so, they've been injecting money into sort of science sport collaborations for the Paris 2024 Olympic Games. So there was this program called Science 2024, Science 2024, and that was kind of to boost science sport collaborations for the French Olympics. They were interested in improving performance in rowing and in cycling. And so I worked on a rowing problem, which is essentially rowing, canoeing, and kayaking. They wanted to know what is the optimum shape of the boats, basically. So this is kind of like a simple sketch of how you arrive to the shape of a kayak. So if you're trying to minimize drag, you could try, first of all, to minimize the wetted surface area of an object. That would give you a sphere. But everyone knows that that's really bad for drag. So if you try to improve the shape to a teardrop, that's hydrodynamic. But it turns out it's really bad for waves. If you try and pull a shape like a teardrop through the water, you'll create a lot of waves. And so you end up with this kind of kayak shape or a rowing boat shape, which is pointed at the front and the back, which is trying to be hydrodynamic and also minimize wave disturbance. So I worked on a project for a while, studying how to find what is the optimum asymmetry between the point at the front and the point at the back, because they're trying to do different things. And it turns out that rowing boats are actually a little bit asymmetric, but it's not known exactly what the optimum asymmetry should be. And then I also, when I was in Paris, I also worked on this problem to do with finding the optimum descent trajectory in a velodrome. So when cyclists go around a velodrome, they do this thing where they kind of catapult themselves down the slope, and then they try and go around the track as fast as possible. And so there's kind of like this classic applied maths problem called a brachistochrone. So it was actually solved by Newton, so it's finding this curve that will take you from point A to point B in the minimum time. And so what we did is we basically took that and used it on a velodrome surface. So we went around the velodrome and measured its angle going around. And then you can create this three-dimensional reconstruction of the velodrome. And you can calculate the path that gets you from point A to point B in the minimum time. So after that, I did a postdoc in Cambridge, working on carbon capture and storage. So completely different now. But so this is perhaps of interest to the Earth Institute. So what I was doing there was I was trying to use applied maths to essentially try and simplify a very complicated problem, which is when you're trying to store CO2 underground, you have these heterogeneities. Sorry, this image has come out a bit blurry, but you have heterogeneities all the way from the millimeter up to the kilometer. So it becomes very computationally difficult to solve that problem. And so I was looking at using mathematical modeling to sort of study how to incorporate large uncertainty into the predictions of how like a CO2 plume would move in a reservoir, for example. So I worked on that for a couple of years in Cambridge. And then most recently, I've been thinking about ice. So this is a work that Gabriel has done. So Gabriel's a PhD student that I'm co-supervising. He's based in Oxford. And he's looking at understanding how glaciers drain through sedimentary basins that sit beneath them. So basically, you've got ice, a big mass of ice, which is itself a kind of fluid, and that's moving. But as it's moving, it's melting, and water is going into the porous medium, which sits beneath that. At the same time, you've also got the seawater, which is intruding beneath. This is over like a very large scale. And so what Gabriel's studying is he's looking at essentially what happens over a glacial cycle as a glacier moves forwards and then moves backwards. What happens to that seawater beneath it? And does that seawater play a role in the heat transfer? Does that seawater change the way in which the glacier is advancing or retreating? So here are some of the things that I'm kind of interested in working on over what you know. Now that I'm here, I'm sort of thinking about what I'd like to work on next. So I've just started my position as an assistant professor, lecturer at UCD. And so these are the things I'm interested in. First of all, I guess in waves and renewable energy, I'm interested in understanding how, I'm quite interested in solar arrays, floating solar arrays, and understanding how waves play a role in their structural integrity. Same with floating wind turbines. Kind of related to that in rowing and water sports, when athletes move their bodies, they cause the boat to shake backwards and forwards. So there's there's an interesting coupling between the performance of the athlete and the waves that they're creating and interacting with. Also interested in understanding how insects move around on ponds, which is actually kind of related to that question. And then in porous media, I'm quite interested in understanding enhanced rock weathering, again, for carbon capture. So like, can we spread building materials onto fields, essentially, to get some of the CO2 out of the atmosphere? I'm interested in flooding also, and understanding how groundwater responds to intense rainfall. And then also kind of like very recent approaches to studying flow in porous media, not from a physical point of view, but from a data point of view. So, you know, now we're starting to get lots of data of flow in porous media. And then can we answer questions about flow in porous media, not from solving partial differential equations, but purely from a data-driven perspective. So I'm quite interested in those sorts of ideas as well. So I'll stop there, and yeah, please feel free to ask any questions.